there. As I said, I'm going to mention this today. I'm going to overview the tutorial. So I'm going to go a little faster, but I'm going to cover some of the topics from before. But before we start, I would like to acknowledge the people that do the work, and particularly the students, Libor, Michael, and Jacob Giles, and also my senior leader, Helen Gomonai, who will be here the whole week. Unfortunately, I have to leave immediately after to catch a plane for this talk, so please talk to her in any ideas that I present here. So the overview is going to be quick in the next 40 minutes. Because I'm talking about spin-orbit torques, and it may not be familiar to all of you, I'm going to review again a little bit of, just rather more quickly, what I said yesterday about how the spin-orbit torques arise, coming from the ideas of the spin Hall effect, and how coupling the spin Hall effect and the inverse spin galvanic effect, we end up with torques that are able to manipulate magnetization, and how we utilize that knowledge to predict the idea of Neel spin-orbit torques to manipulate spintronics, antiferromagnetic spintronics, and a little bit of overview of why antiferromagnetic spintronics and what we mean by antiferromagnetic spintronics is. And the last part is just a work in progress that we're trying to finalize here, so it will be a little more sketchy on idea of merging topological Dirac fermions and antiferromagnetism and Neel spin-orbit torques. So as I mentioned yesterday, the spin Hall effect, which was observed in 2004, also comes at the same time as another effect, the inverse spin galvanic effect. The spin Hall effect itself, it generates a spin current. So as you have a spin-orbit coupled paramagnetic system here illustrated in 2 dimensions, and you accelerate it, there is a coherent precession. This is the idea of intrinsic spin Hall effect in this case, not this, the asymmetric scattering from spin-orbit coupled impurities. That protests some of the vectors going forward and to the right down, the ones going to the left up, and therefore it creates a spin current, spin flow. You can see the experiment in this case in p-doped gallium arsenide, where you look at these p-n junctions in each side and you see opposite photoemission coming out when they're combined. But in the exact same experiment, the exact same setup, if you look at the p-n junction looking at now in this direction, on the plane, not out of the plane, so this case was out of the plane, but this one is in the plane. In this x direction, if the current is flowing in the y direction, you see a net polarization arising from the fact that in this case, I'm only illustrating this with one of the bands. Keep in mind that there's a second band that goes in the opposite chirality, but with less electrons. You end up, by populating this guy to that side, when you generate a current, you end up with an in-plane polarization type. These two effects are giving rise to the new ideas of spin-orbit torques that were observed first time in bilayer systems, for the first time in terms of switching the magnetization. There were some prior experiments that show that these effective fields appear there, but these were the first time that they were actually shown to be able to flip the magnetization by running a current not by doing the typical spin transfer torque, which is in a tri-layer system when you run the current from a ferromagnet to a normal metal to another ferromagnet. But in here, you actually are using a paramagnet below the ferromagnet. You drive the current below this ferromagnet, and there's a torque that is observed on this ferromagnet that flips. In this case, this is perpendicular, out of plane anisotropy that flips up and down. And this one, it was in plane, but you're able to flip it side to side and be able to detect it with the amplifier. In terms of the physics of it, there's 2 things that come into play, or the origins that you can have. One of them is going to be this idea of this non-equilibrium polarization arising from the inverse spin galvanic effect, that then if you couple with the magnetization, it gives a torque. So it's going to be m cross delta s. And then the symmetry of it depending on the dependence of this non-equilibrium polarization on the magnetization direction. If it's independent, it will be a field-like torque, and if it depends on magnetization, linearly magnetization, it will be a dissipative-like torque. In the other case, if it's just arising from the spin Hall effect, which was the interpretation of Bergman et al. In Cornell groups, in that Ralph Cornell's group, you run a current here. The interpretation was that you can see that it is primarily dissipative-like, or antidamping-like, then this would have this form m cross n cross delta n, when this n is in this parallel direction. And this one is of the form of the Zlochevsky clone, which is naturally antidamping. And it was interpreted to be that this is arising from the spin current generated from the spin Hall effect that goes into the ferromagnet and is able to switch it. The experiment itself, as I explained yesterday, it was actually done by what is called inverse ferromagnetic resonance experiment, FMR for short, where you actually look at this DC voltage that you generate as you drive a gigahertz current through the sample, and through the equations in here, you just invert this delta S based on the line shape, analysis of the line shape here of the resonance, which in this case, if you break it apart into the symmetric and antisymmetric component, if you look at the amplitude of it, it has a natural dependence of sine 2 theta for the symmetric one, which is proportional to the perpendicular out-of-plane magnetization, or effective small magnetic field, and the in-plane, which is the field line, will have this other dependence with sine of 2 angles, sine and sine multiplied by the x and y component, and here, by divided by these forms, you're able to extract each of them independently. Just as I mentioned, there's two types of torques in these Valère systems. You actually have, yes, this one is coming naturally, the fact that you have the spin current injected, and naturally you will end up with a field-like and antidamping-like, primarily antidamping-like, but there can be a field-like if the ratios between the spin and lifetime and the exchange, the precession time of electron is finite. But in here, what it was not really understood too much, it was really believed at the beginning, that it was primarily field-like for the Rashba ones, because this in-plane polarization is effectively very independent of magnetization. And this is the thing that recently we showed, that you indeed actually have, they could have as a strong component as this one in this type of physics. So just by looking at the symmetry, you could not really tell. If you look at the extrinsic components, yes, in this case, this is the field-like component, as I mentioned earlier. By the way, I want to make sure that people time in here. Then you have the antidamping, but then you had to actually also worry, just as we worried in the spin Hall effect, in the intrinsic spin Hall effect, you will have a component arising from the equilibrium distribution function at the non-equilibrium states. Essentially, it's kind of like a reactive term in the linear response that appears both in Kubo formula and also in non-equilibrium Green's functions formalism, where now you replace this spin current by a spin operator and look at the non-equilibrium induced polarization by a current in the system. If you do so, just as I mentioned yesterday, if you look at the picture of the spin Hall effect, and you now add to this overall the structure of the Rashba, you add a strong exchange interaction with the magnetization, so it primarily lines up, or in this case anti-lines up, because I'm already looking forward to the experiment of gallium manganese arsenide, with the magnetization, the spin. Then you actually have a system that is primarily pointing in that direction, in the opposite direction, but not following this chirality too much. But as you accelerate, the only field that is going to be extra as the electron changes its momentum is the one arising from the spin-orbit coupling, and therefore it's going to just the same thing as this one in here, and it's going to process it down, creating a non-equilibrium polarization out of the plane. And if you act, but this one, in this particular case, this delta Z, as compared to the one in plane, does depend strongly on the direction of the relative direction between magnetization and electric field. Because if you have it perpendicular in this case, as you can see, it will be zero. Because as you accelerate, this extra effective magnetic field that you see away from equilibrium, it just points in the same direction as the spin, so there's no precession whatsoever. So this delta SZ would have this cosine of theta angle dependence if you have the Rashba-like symmetry for the linear part of the spin-orbit coupling. In the experiment itself, we look at gallium manganese arsenide, or they look at the gallium manganese arsenide, just to be clear, the experimentalists, where you have the shear strain gives you the Rashba, the compressive strain, which is predominant in this system, gives you Dresselhaus. So the next thing with the Dresselhaus, that it also has this crystalline anisotropy where you can now identify things much more clearly. Because here, depending on the direction of where your current is, you have a different angular dependence. It is not as simple as it's just simple angular dependence. They actually experiment and theory comparison have some higher harmonics arising from the interaction of this linear component and this Q-square term that is in the p-doped systems of gallium manganese arsenide. But it's effectively, the nice thing about these type of experiments, when you just have now a single ferromagnet, not a bilayer, but a single ferromagnet with inversion symmetry broken, you just have, the only origin itself is the inverse spin harmonic effect. So this is what I would call a pure spin-orbit torque that you're observing in this case. It's not a combination of spin Hall effect and a spin transfer torque. Okay. Now this was of course observed for systems gallium manganese arsenide and the dilute magnesium semiconductor, and in the case of in this case both the field-like and anti-damping one were of the same order. If you look at now at other ferromagnetic systems with broken inversion symmetry, in this case you have to go, for example, to the family of Heusler's. This is nickel manganese antimonide. You do the calculation, exactly the same calculation that I just showed you. Both the field-like and the typical way we try to do the calculations is by doing both linear responses, Kubo and non-equilibrium, because they both have different strengths. In the Kubo, you treat disorder a little more trivially by just broadening in the scattering formalism. You can put disorder a little more extra and takes account of all of the effective vertex corrections, etc. for the theorists. But they don't compare well. It was about the same results when they do it. And they compare well to the experiment itself that was done. And in this particular case for nickel manganese antimonide, it's dominated by the field-like component, and there's not so much anti-damping component in this particular case. And these things will vary from material to material. It really depends on where these band crossings is, on the band structure. So there's a lot of play to maximize or minimize the effect of one or the other. Now, so this was just a quick interaction to introduce the idea of remind you of the spin-orbit torques and what they are. Now, then the next thing is to think about extending some of these ideas to antiferromagnetic spintronics. And here I wanted to introduce the idea of what it is that we mean by antiferromagnetic spintronics. It's an area that I think is growing much more interest. It's of course has a long history. Antiferromagnetism studies have a long history, particularly here in Ukraine. There's a long tradition here of that. But it is new ideas, particularly very, very new ideas over the last couple of years that were realized about torques that people could not imagine that they could exist. In this case, these Neel spin-orbit torques. Okay. It's just a fancy little illustration that I showed you. And then they have some reviews, by the way, particularly the recent one by Thomas Youngworth in Nature Nanotechnology, and also the one by Glatzman, Sean Choi, Ono, and Zerkovniak here as well, that I'm not sure will be published. Do you know, Yaroslav? Okay.
Under review.
Under review, but do you know where they submitted to look for it?
Reviews of modern physics.
Okay, well, okay. So you can find it there, hopefully at some point in the next few months. So this one, they're covering a slightly different perspective, so this is good to see them both. They were written a little bit like that to give you both different overviews. But the idea here is to begin to use antiferromagnetics as active elements in spintronic devices. Before, there's a lot of history of antiferromagnetism, of trying to look at these things as passive elements because they were difficult to actually manipulate. Of course, the whole technology that we have here depends on ferromagnetism. But ferromagnets, there's not that many of them that are useful. We depend, I mean, each of you guys are paying about every human in the planet is paying about 6 to 10 euros per year for ferromagnetism technologies, 35 or 40 billion industry, so you just make the numbers. But it is based on like 4 or 5 elements or materials, that's it. There's not that many of them, but they're very, very useful because they're easy to manipulate. But they have some drawbacks, they're actually affected by magnetic field. The speed are limited, particularly to the scales, to those ferromagnetics that are available. It's material to material, of course, as we mentioned yesterday, there was a discussion that with Leonid asking about the different relative scales. But in here, the problem with the ferromagnets, that they're not easy by external magnetic field to manipulate, of course. They're very, very insensitive to magnetization, so if you can make them active, this is something that, from the point of view of this type of devices that are what you call radiation hard, is quite good. They're naturally faster from the point of view that their exchanges have this idea of exchange enhanced phenomena by having these two things coupled, and most ferromagnets, the frequencies, the resonance frequencies on the order of hundreds of gigahertz of terahertz. And this actually, from the point of view of this of course arises from us trying to understand the magnetic semiconductors. If you try to do ferromagnetic semiconductors diluted, there's not that many parent compounds that you begin with that have a very high TC. Whereas the parent compounds in the semiconductor area, there are actually that many that the Neel temperature already starts high, so you have a hope of going low. For example, in gallium manganese arsenide, manganese arsenide itself didn't have a very high transition temperature TC. So the hope that you would actually get to room temperature was a bit too optimistic, to say the least. So the first thing to think about is, okay, how do you manipulate the ferromagnets? These very interesting materials that Neel himself said that they're very interesting but useless. Okay, we're going to try to show you that they're not that useless. But first of all, just utilizing this is the first example, easy example that was done by looking at creating, this in this case is not active manipulated memories, but memories that you can read and write like in a credit card, but they're totally insensitive to magnetic fields. And you can do this with iron rhodium, because iron rhodium has a property that above some temperature you're ferromagnetic, below that temperature you're antiferromagnetic. So when you actually hit it in a field, you're able to cool it down, and it will line up in the Neel order parameter will line up anti-parallel to the ferromagnetic one once you cool it down in the transition from ferromagnetic to antiferromagnetic, as I show here. Okay, so you're cooling this in field and it just goes from there to there. And then you can write there, you can use anisotropic magnetoresistance, because anything that is proportional to the effect that is goes to the square of the magnetization rather than linear magnetization will also be present, just like Neel told us in his lectures, actually in his novel lectures, that you will be able to observe such an effect. Both will be present in ferromagnets and antiferromagnets. So in here, just by simple ohmic measurement, just a resistance measurement, you can detect in which direction you've written that bit. Whether it's in this direction, the Neel order parameter of that direction, so you can see this red and blue, okay, between the two, thank you. And then you can also see that in this case is very sensitive to magnetic fields. Here I put it up to 1 Tesla. In reality, you can go to 6 or 7 Tesla. This is what the experiment had done, and nothing happens. So your whole credit card will not be erasable in this case. Okay. But what I want to do is to actually not just do some passive memory, but think of the idea, just as I mentioned, the spin-over talks and ferromagnets, where we're trying to go to active magnetic random access memory devices, or at least that's the long idea that we write in the proposals. From my perspective, I just find the physics fascinating. Then we have to try to make antiferromagnetic spin-orbitronics, where you try to use this idea of a spin-orbit coupling that I just told you about in terms of the spin-orbit torques, and think of them in the context of antiferromagnetics, antiferromagnets. So, can we type, what type of current-induced polarization can we generate? And the first one, which surprised us, but it was an insight that we had, looking at the notion that spin-orbit coupling, it is a local phenomenon in a sense. It's coming from these local, strongly bounded electrons that then couple with the conduction electrons to generate this spin-orbit coupling. Meaning that if now I look at a centrosymmetric ferromagnetic system, antiferromagnetic system, actually forget about the antiferromagnetic component for the time being, if you don't mind. Just ignore the fact that you actually have, in this case, manganese to gold is an antiferromagnetic layer of antiferromagnet. If you look at this unit, okay, you decompose it into 2 sublattice. This actual structure is created of 2 inversion symmetry broken structures, okay, coupled together. So you have 2 partners with opposite inversion symmetry. Okay, here you can see how I've broken it up into 2 units where the gold atoms in opposite sides. Okay, if now you look locally at the unit cell, so inside that unit cell, you actually, if you do the calculation, or we did the calculation, even without a spin-orbit, even without any Neel order, you end up with a type of Rashba-like spin-orbit coupling orientation. This is actually, Alex Zunger also saw that in some of his calculations about the same time we saw it, where you actually, he called it a hidden symmetry, hidden spin symmetry or chirality within the unit cell. Now, initially we thought that it could have, because the story of it, I can tell you that it originated by doing the calculation first with the spin-orbit, with the Neel parameter there, and so we thought that the inversion structure, the inversion was broken by the Neel order, but in reality it's not. It has nothing to do with this Neel order or not. It's very, very similar to the inverse galvanic effect. It's just that it's quite local, because now in this case, when you run a current through here, you actually will end up, and as I showed you in the calculation, with opposite generated polarization in opposite sublattices. Okay? So if you run a current through this system, you will end up in each of the atoms with some small polarization point in opposite, where the direction of the polarization depends primarily on the current direction, just as the in-plane polarization that I showed you, the inverse galvanic effect, depends only primarily on the direction of the current. Okay? Now, this of course was never expected, because anything that can be changed in the, this is what Alexander also said, that it just didn't, so we can never see it because it varies in the order of the unit cell. It's within the unit cell, so you will never be able to have a measure of that. We will never have an effect, except, of course, we were thinking from the point of view of torques. Once you couple to the antiferromagnetic order parameter, this becomes essentially like an additional added anisotropy once you have a current. And this is the type that can switch you. And here, just to show you the calculation itself that we did in 2014, where we just do the linear response calculation and look locally. You can do this in ab initio calculation and time binding calculations. You can look locally at the polarization generated by the current at a particular in this case, per current of course, it's linear in the current. And here, if you run the current along the x direction, in this direction, you'll end up primarily within the A sublattice in say positive, in the B sublattice in the opposite, and along the x direction, along the current, almost nothing. Okay? And here to illustrate that it's independent of the angle, these angles in here, this is the degree, the angle relative to the z-axis of the Neel order parameter. So there's some small oscillations, but very little. This averages to 0 in this case, and it's pretty much constant for the other ones. Just as I suggested in terms of the illustration, what am I talking about? What am I saying? It's effectively, it's like as if locally, domestically, you've wound out some solenoids with opposite chirality in the opposite sublattices. So when you run a current, you effectively are just switching directly your antiferromagnet to the opposite side, 90 degrees, of course. You cannot switch it the other way. The experiments themselves, were done in copper manganese arsenide, which is the same band structure, the same structure as manganese to gold, but easier to grow, or they managed to grow it. And it is important to understand that this was a measurement done particularly by anisotropic magnetic resistance. So you run a current in this direction, and then you run a current in the other direction. In this case, there are actually 6 directions, so more than that. And you can see that if you run a current in this direction, the resistance is switching between one and two. No, the other two resistances are switching because the Neel order parameter is switching. Okay, in 90 degrees, and it's not switching, by the way, directly in a single domain. At the moment, it's actually switching in some multi-domain, as you can see here. The pulses. It's gotten a lot better now in the latest versions, I think. The pulses are much faster and much more efficient. But at the time when they first did it, they would have to run a current first at certain times, a certain number of pulses, and you would end up aligning more and more of these domains of this multi-domain. And you could see this directly. This is indirectly through the anisotropic magnetic resistance, but you can see it more directly by imaging through XMLD and spectroscopy, where you run the experiment. So this is the same experiment as this, as you can see here, and you run the current in this case kind of like from here to there. So you have one component that is in the x direction, another one that is in both, and another one that is in this direction. And you can see that when I don't have the movie of it, but when you start running the current, everything is kind of grayish. And then when you run the current, this becomes black, this becomes white, and this becomes kind of grayish. And you can also see the calculations that were done between experiment and theory for the different alignments that agree fairly well. So we're very confident that this is indeed this AMR that you're seeing, that you're switching between one and the other, that is very sensitive to magnetic fields as well. It is arising from this realignment of the Neel order parameter with all the checks and balances that they were able to make. And that was some part of the experiment. This is the experiment done led by Thomas Jangworth and the team of Nottingham and Pro, who's been really leading the field a lot in these ideas. And then one of the lucky things that they had as a team, that they have a guy, Xavi Marti, part of the team, whose brother-in-law owns the technology company. So he was able to put this device, this copper manganese device, into a chip that is readable, and you can actually read and write a few bits in this system. So this indeed that I showed you yesterday, this was created only a few months after, or a couple of months after, this circuitry, where this is the first antiferromagnetic random access memory, maybe? Essentially writable memory just by electric fields of copper manganese hastide. Okay, at room temperature, obviously, because we couldn't put this in the cryostat. Now, so this is exciting from that point of view. The technology, the possibilities are there, and it's the first time that I see. I mean, for me, it's quite exciting to have seen that 2 years ago proposing it, then a year later seeing it, and then almost immediately an actual possible device that you can plug in a computer. A useless device at the moment, but something that I think, of course, in terms of pace of technology development, have gotten people quite excited. You also have, from these Neel spin-orbit torques, because they couple fairly well to the Neel order parameter, they're very, very useful to move domain walls. In this case, domain walls from antiferromagnets are distinctly hard to observe, so we're not, that's going to be a little more challenging to see. But one of the important things that Helen taught me is that this itself is going to create a panderomotive force, meaning that this force itself is kind of like a pressure force of more energy on one side than the other in these domain walls, such that you don't depend so much on the nature of the domain wall, whether it's nailed or block-like, and therefore it is much more efficient in terms of driving cohesively and fast these domain walls. And the speed itself, I mean, it's nothing to do too much in efficiencies to that to do with Neel spin-orbit torque, but the ultimate speed is because it's 50 kilometers per second, which is a huge, huge speed. It comes from the fact that the magnons themselves, the speed of the magnons, and these antiferromagnets that we're considering, is much higher than ferromagnets. So it's a natural velocity. It's not something that the torque itself is giving you. It's the antiferromagnetic one that is giving you. We're just giving you an efficient way to actually generate that motion. And maybe she will have any questions you have. You have the ultimate expert here in the audience, and from Ukraine. Now, the one that I was, the Neel spin-orbit torque that we showed and experimentally was observed, it is what you would maybe term, in the terms that we had learned from spin-orbit torques, from that jargon, from that language, it is based essentially, I would call it field-like, because as I mentioned, it doesn't depend strongly on the relative direction of the Neel order parameter and the current. But you will have another one, and this one, for example, if you have now a spin-orbit coupling that is homogeneous, so both sublattices see the same spin-orbit coupling. This could happen in a bilayer system with an antiferromagnet and a heavy metal. If you do that, both sublattices see this effectively the same spin-orbit coupling, so they would cancel each other out. You would not see any constant, any Rashba-like Neel spin-orbit coupling like I mentioned earlier in this type of setup. But just as you would expect, or I would expect from my experience with the spin Hall effect and the other calculations in the spin-orbit torque, you do have a strong, and here I hesitate to call it dissipative-like because the equations of motions are not the same, okay? They don't have the same consequences. But in this case, you have a Neel order parameter, a stagger field that you generate, a non-equilibrium stagger field that you generate, that does depend strongly on the relative direction of the current and the angle of the Naylor parameter. It is much more complex. We don't know exactly the consequences. We're still studying some of the ideas. Such torque, what would generate in terms of the dynamics? Could you actually even switch this Naylor parameter deterministically by this type of torque? It may or may not be possible. You have to maybe be in particular regimes. It's not as simple as in ferromagnets, as I've learned a lot, and Helen Gomonai has taught me a lot over the last year and a half that he's been in our team. So in a sense, this is something that we hope that eventually may be observable and useful. But one thing that we do know, and this is definitely also coming back, 5 minutes perfect, that would be good, is that they're going to be much stronger because you have very little this gap compared to the ferromagnets, which gives you a natural gap. And if you just look at the ferromagnet and antiferromagnet, there's a couple of orders of magnitude difference in the type of strength of the torques. Just natural from the fact that they come from these interstellar contributions. Now in the last 5 minutes, I just wanted to give you a brief idea of something, a new direction that I hinted as well yesterday, which is the idea of varying topological Dirac physics and antiferromagnets with Neel spin-orbit torques. And this is these two areas that have been developed since 2004, a bit in parallel, sometimes talking to each other, but much more fairly independently, of Dirac physics in solid-state materials. And this is strong Neel spin-orbit torques. And this is really, literally the idea of Lewis Michael. This is a brilliant student, one of the most brilliant we've had, that really came and said, I would have to like to pursue this idea. And we said, okay, great, let's go, let's do it. And this sort of marries these two ideas, because the two are independently okay, but can we actually have them together and manipulate them and actually create these switches between different topological phases just by driving a current. The relativistic physics, the topological and semimetals and spin electronics effects, come, of course, the topological aspects of Dirac and Weil fermions from these two types of fermionic, Dirac type of fermionic systems. The Dirac and the Weil having a slightly different symmetries. One of them having four degenerate and the other one being double degenerate. But this is type of physics that now has been led a lot by theoretical works that then are observed immediately after for the mission experiments, particularly looking at the band structure, where you can see all these crossings created that in some cases are protected. You have Dirac semimetals, you have Weil semimetals, in now materials that have been well observed. And it's exciting to people also because you can have both types of these priorly exotic high energy physics into the system, okay, 3 dimensions now at this stage as well. But one that, for example, can give some practical, or is believed that can give some practical results. And here I give you an example that is exciting because here's the use of cadmium arsenide grown by the team of Claudia Felser. And this is something that you just grow in a beaker, okay? You just grow this sucker on a beaker, and you end up with mobilities much higher than you could do in MBE machines. You have a mobility here of 10 to the 6, 10 to the 7 inverse ohms per centimeter square per second. And these are huge, enormous. In here, the interpretation that they may be from this protected state or maybe protected states in terms of laser scattering affected by the disorder. It's still, early days to tell, but I think in this case this is exciting from that perspective. But can we control these relativistic fermions electrically? And this was the idea of looking at the physics of course, graphene is the ultimate system that you started this idea of topological one systems in solid-state systems. But looking at these two copper manganese arsenide, you do have symmetries that overlap. The PT symmetry, which is the one needed to have the crossings, is there. Also the fact that you need 2 elements per unit cell, as well as here, arise naturally in this structure. And we were able to identify, particularly in here, to understand the crossings that we actually observe here. I will show you the calculations that I have only 2 more minutes. In a very simple, effective Hamiltonian, showing that you can identify this glide, I forgot the name, glide, okay, there's a mirror plane and then you move it at half a unit cell. This is called glide symmetry. It's a non-symmetric symmetry, as I mentioned. It involves a point symmetry and translation. And this effective simple model that you can map it to this advanced structure in 2 dimensions. You can also do the 3-dimensional version. you can analytically solve it in the presence of an Neel parameter. And in here, this extra symmetry that you have of this glide mirror plane symmetry allows you to manipulate the gaps depending on the direction here of the Neel parameter. So some of these gaps will be protected in the presence of a spin-orbit coupling. This is with a spin-orbit coupling, depending on the direction of the Neel parameter, and the actual symmetries that allow you for this also allow you for Neel spin-orbit torques. And here, this is the actual calculation of the system, the actual ab initio calculation, showing you how the gaps can actually be changed in changing the relative direction of the Neel parameter, and allowing you to actually, just by moving the Neel parameter in different directions, to go from an insulator, effectively semiconductor, to a half metal or some different versions depending on where your crossings are. So with that, I think that this is the summary of what I talked about. I think right on time. Where I introduced, reminded you a little bit of what the spin-orbit torques have come about from the spin Hall effect and the inverse galvanic effect that you should always think in conjunction. How it gave you spin-orbit torques, how from that we've created these Neel spin-orbit torques, and how this type of physics can be utilized to merge with Dirac physics as well. So thank you very much for your time. And,
so for spin Hall effect, it's knowing that disorder is important. So for example, if you deal with spin Hall effect variable coupling, you have to with disorder. Is disorder important in antiferromagnetic systems?
Okay, let me address the first comment, which is actually not quite so. It was very important, and first was actually part of this first story of the spin Hall effect. The spin Hall effect, when we first proposed this idea of intrinsic spin Hall effect, I did a mistake and I didn't follow Einstein's advice, which Einstein told us to do things as simple as possible but not simpler. So I chose the linear Rashba 2D model with parabolic bands as a good example, making the mistake that in this particular model, just this particular model for particular symmetries, the disorder actually kills the effect. So the illustrations that I showed you 2D. For any other system, 3D, anything that we have found, platinum, all the other ones, tantalum, the disorder is not so strongly affected, very similar to an anomalous Hall effect, where there's a large range of metals, where you have what we call now, not that it's not affected, but it's scattering independently, effectively, the system of the signal. So in this case, it's not so strongly dependent on disorder. Particularly in this particular case, the Neel spin-orbit parameter that I talked to you about, it is actually dissipative-like. So it is this Rashba, this field-like component is proportional to tau. So this one, the one that depends on the angle directions, that should not be so dependent on the disorder, because that's the one coming from these intercell band connections, unless of course the broadening and the band crossings are of the same order. Then of course we will simply kill it as well.
So you mentioned this very clean material that has this high mobility. I forgot what the...
Yeah, I don't know the name, but I can show you. Yeah, it's
so why is the mobility so high? Is that so pure, or is it
no? It is grown on a beaker. This is not MBE grown. That's the thing that's magnificent. In here, the calculations show that you have here vital points near the Fermi surface, and it's believed. I mean, this is just a conjecture at this stage that maybe this kind of protection is similar to why the high mobilities in graphene, you end up with these enormous mobilities in something that you've grown in a beaker. And this is crystal grown. And so yeah, when she showed it to me last year, it was really, I was like, wow, I've never seen that. I mean, these are really extremely high mobilities.
So is there some other physical effect that you see? Is there some quantum Hall effect? Or?
No, definitely not. This is the only thing that data that they had at that stage. It was that, the mobility came from the Hall effect that they measure, of course. It's a Hall effect mobility measure, if I remember correctly. But yeah, to me it's surprising. So it's just a tantalizing possibility, I would say, at this stage. But for me, it was like, wow, okay, it could be practical. Because we've talked a lot about this topological, that. Topology doesn't really protect you that much if there's a lot of disorders and a lot of things. If you break all the symmetries, So you have, the stability similar to skirmions. So you have topological protected. It turns out that skirmions are a little bit fragile, okay? the solid things that stabilize these things. So yeah, that's to me it's a puzzle, and I think it's exciting.
Okay, well, maybe we should.
Thank you.
Thank you.